So what are the higher levels? Well, that's the level of ideas. What is it that we did here? We expressed what we did explicitly, right? But translation doesn't work. So we have to give a different description. What could be a different description? No, can you explain in words what we did?
Find the equation of the tangent line.
Find the equation of tangent line. So let's do the description here. Given original input x1, find the equation of tangent line. At the point x1. And then what? So equation, let's call it T1 of x. T1 of x, probably y equals T1 of x, right? Equation of the tangent line is like that. So once you found the equation of the tangent line, what do you do?
The value of x where y has the value you want.
So you solve. Remember, you want to solve this equation. Right? So you solve another equation. You solve the equation T1 of x equals 0. And solution of that is called x2. And you hope that x2 is much better approximation. And then you come back. Now, can we translate that? So now I have to start with a triple. Given the triple E1, capital D1, L1, what do I find? What's the analog of the tangent line? The gradient, if you know what it is, right? But in that multidimensional setting, I don't know if the word gradient is even appropriate for that setting. I just don't know the proper terminology in this particular setting. So, but what is it? What is it that you want to find, and why is it analogous to equation of the tangent line?
Sum of the partial derivatives.
Sum.
Vector along the line.
Say again?
The vector along the line.
Direction of the greatest rate of change.
Direction of greatest rate of change of what?
Range.
Yes, well, it's hard to think about rate of change of the pair. Right? That's the problem. That's the problem about bringing this idea of gradient. We really have to deal with the change of the pair, and there is no concept of derivative of or rate of change of this pair with respect to any of those three variables. So we really have to analyze what does it mean to have a tangent line in multivariable setting. Can you say it differently? Yes, well, what is the problem? where does this tangent line concept belong? Does it belong to the domain of the function? Well, it doesn't belong to the domain, it doesn't belong to the range. It belongs to the graph. Well, it's somewhere there in where? It's not in this plane. It's not in that 3 space. It's somewhere in that 5 space. The space where we cannot even imagine. So instead of thinking geometrically about an object in that 5-dimensional space, can we think algebraically? Can you tell me algebraically what happens here? What is it exactly that you are finding in algebraic terms? What kind of equation is that algebraically?
Linear equation.
Linear equation. How is that related algebraically to the function?
It's always the first derivative.
Say it again.
We always use the first derivative to find the tangent line.
Yes. So what's the relation between t1 of x, the thing we want there?
Oh, it's the first 2 terms of the Taylor series, if you want to look at it that way.
Well, do you want to look at it that way? Isn't that an algebraic way of saying what we are doing? So this is the first 2 terms of the Taylor approximation of that function. Right? So t1 of x can be written explicitly algebraically as f of x1 plus f prime of x1 times x minus x1. And that right-hand side is approximately f of x, because it is a part of Taylor series.